When galaxies merge, their gravitational tides unravel the old geometry of stars and gas, reshaping orbits as if the universe itself were a restless sculptor. A sun that once circled quietly in a stable spiral arm can be pulled thousands of light-years inward, flung outward to the halo, or even captured into a tidal stream stretching like a cosmic ribbon. Each planet bound to such a star follows along, carrying its fragile atmosphere into regions of space where the radiation is harsher, where gas flows are denser, and where supernovae spark more frequently. Worlds that once basked in relative calm may find themselves under skies lit by violent bursts of ultraviolet light or swept by streams of high-energy particles, while others suddenly sink into more quiescent zones where the night grows darker and colder. Collisions are not sudden explosions but rather grand choreographies lasting hundreds of millions of years. During this slow ballet, disks are distorted into elongated bars, halos are stirred, and long tails of stars and dust peel away like luminous scars across the blackness. These tidal bridges are not just ornaments, they are escape routes for stars that abandon their native galaxies, becoming wanderers between systems, dragging entire planetary families into intergalactic exile. For a planet, migration across tens of thousands of light-years means adapting, or failing to adapt, to entirely new stellar neighborhoods, new cosmic weather, and new gravitational rhythms. Some may encounter denser molecular clouds that trigger cometary bombardments, altering their climate and oceans, while others may be shielded by dust lanes that reduce starlight and plunge surfaces into colder regimes. The central regions of merging galaxies grow especially volatile. Gas, once leisurely circling in the outer arms, is funneled inward by gravitational torques, feeding starbursts and supermassive black holes. These central furnaces ignite with fierce luminosity, turning galactic cores into quasars or active nuclei that flood entire regions with radiation. Any planet caught in such a migrating orbit toward the heart of its galaxy may find itself bathed in deadly X-rays and gamma rays, stripping atmospheres bare and leaving behind sterile rocks. Yet paradoxically, these same bursts of energy seed surrounding space with heavy elements, scattering carbon, oxygen, and iron that future generations of stars and planets will inherit. Thus, destruction and creation are woven together, migration acting as both a threat to life and a catalyst for its eventual rebirth elsewhere. When two galaxies fall toward each other, the scene looks serene from far away, two swirls of starlight drifting closer, but up close the physics bites. Long-range tides stretch each disk, excite bars and one-armed lopsided waves, and torque the gas so efficiently that material which spent billions of years circling at leisure suddenly loses angular momentum and rushes inward. The first pericenter passage lights compression ridges along the arms where shocks ignite star formation. The second passage is rougher, with bridges and tails unfurling for hundreds of thousands of light-years, record of momentum traded and orbits rewritten. A single star can have its guiding center shifted by tens of thousands of light-years. In phase space the move is even larger, as vertical oscillations thicken and epicycles swell. Its planets come along for the ride, dragging atmospheres into new radiation baths and new bombardment regimes, as if a family had been uprooted overnight and dropped into a different climate, at a different altitude, under a different sky. The immediate hazards are environmental rather than directly tidal. Galaxy-scale tides are too gentle to tear planets from their stars except in the crushing densities of a nuclear starburst, but the neighborhood changes in ways that matter. A migrated system that sinks toward the inner kiloparsecs encounters a higher supernova rate, stronger ultraviolet backgrounds, more cosmic rays, and hard X-ray flashes from high-mass binaries. Inflows feed the central black holes, feedback from the active nucleus raises the ionization field and drives winds that carry dust and metal-rich gas through the disk. An atmosphere that was marginally stable to photochemical loss can tip, hydrogen bleeds to space faster, ozone layers thin, cloud decks reorganize. In contrast, a system kicked outward toward the dimmer outskirts may see the radiation budget relax while the frequency of molecular cloud hits on its Oort cloud analog drops, cutting the long-period comet traffic. The climate can cool, not from a weaker host star, but from a gentler galactic sky. Tails and bridges are not decorations, they are cold dynamical ledgers. In them are stars flung onto elongated paths by resonant encounters, plus gas that has been sheared into filaments where turbulence and magnetic fields seed new clusters. A star caught in a tidal tail can spend hundreds of millions of years in a thin, low-density corridor, safe from giant molecular clouds that would otherwise stir its comet reservoirs, but exposed to intergalactic ram pressure as the tail moves through the halo. On the return, when the tail rains back, the same star may plunge through a dense, shocked shell where cloud collisions are common and the cross-section for perturbing distant icy bodies spikes. Planetary climates, which integrate many small forcings, feel these passages as epochs, extended warm periods punctuated by bombardment spikes, or long winters with clearer skies under a thinner cosmic ray haze. Inside the merging pair the gas obeys torques more than gravity's poetry. Non-axisymmetric patterns, bars, spirals, ovals, transfer angular momentum outward, so that tens of solar masses per year can dive toward the core in a major merger. There, up, bars within bars, cascade can drive material to parsec scales, feeding the accretion disk of a supermassive black hole. The core brightens into a Seyfert or quasar phase, and the surrounding 1,000 light-years bake in a continuous day of ionizing light. If a migrating star's new orbit grazes the circumnuclear ring, its planets will meet a rain of energetic photons and a denser sea of hot plasma. Even without an active nucleus, starbursts alone reshape the medium, hundreds of supernovae carve chimneys, launch superbubbles, and lace the region with magnetic fields that guide cosmic rays. The interstellar weather report flips from scattered clouds to gale warning. The stellar dynamics are a story of violent relaxation, a collective shuffling of energies in which no two stars collide but every star feels the changing potential. After a few dynamical times, the sharp memory of the original disks blurs, angular momenta are mixed, and the remnant begins to look like an elliptical, with a pressure-supported stellar halo and a hot, X-ray glowing atmosphere. Not all memory is erased. Shells, concentric ripples of stars on nearly radial orbits, fossilize minor mergers. Kinematically decoupled cores spin one way while the outer body drifts another, a sign that gas flowed in, formed stars, and locked in a different angular momentum. Planet-bearing stars trapped in these structures inherit their fates, shells sweep them through the remnant's outskirts on elongated tracks with long periods of cosmic quiet, decoupled cores keep them embedded in dense bulges where close stellar passages are more common and tidal nibbles on wide planetary orbits add up. Because the gravitational drama runs slowly, cumulative effects dominate. Repeated crossings of spiral-like shocks raise the vertical energy of stellar orbits, disks puff into thick disks with larger scale heights, lifting planetary systems above and below the midplane where dust extinction is lower but cosmic ray exposure can be higher. Encounters with giant molecular clouds act as random kicks, each one is a dice roll for the Oort cloud, for long-period comet showers, for subtle changes in insolation via impact-driven aerosols. Over tens to hundreds of millions of years the statistics write a climate history not possible in a quiet galaxy, more frequent extremes, followed by long recoveries in new baselines. The planet itself has not changed star, but its galaxy has changed neighborhood around it. Some migrating stars are expelled entirely. Three-body dances during the merger, especially around the binary that the two supermassive black holes form, can fling stars to intergalactic speeds. A small fraction of their planets remain bound, the rest become free floaters, worlds without suns, cooling through the dark on internal heat and radioactive decay. Those that stay bound to their stars but join the intragroup medium live under a thin fog of scattered starlight and a trickle of plasma. They are shadow dwellers between galaxies, safe from supernova storms but starved of heavy element dust that would otherwise seed their skies. The merger, in this way, builds not just a single remnant but also a diaspora of systems drifting in the territory between. Gas physics decides whether the outcome is quenched or reborn. If the halo is massive enough to shock heat fresh inflow and if the black hole's feedback is sustained, the remnant's cold gas supply dwindles and star formation grinds down. The galaxy reddens, the nights above its planets darken, bombardment quiets as giant clouds become rare. Alternatively, if gas survives in the outskirts or rainback from tails continues for gigayears, the remnant grows a new disk. Metal mixing during the merger flattens gradients, outer regions become more enriched than they should be, inner regions less extreme. Future planet formation inherits this chemistry, rocky worlds form more readily at larger radii than before, volatile inventories shift, and the menu of minerals available to geology changes. Migration thus edits not only the climates of existing worlds but the ingredients of worlds yet to come. Magnetic fields and turbulence, often treated as background, are active players. As gas is stirred by tides and shocks, its turbulence grows superalfvenic. Dynamos amplify large-scale fields that thread arms and bars. Cosmic rays ride those fields, diffusing unevenly. One side of a migrating system's path may see higher particle pressure and different cloud ionization than the other, nudging cloud microphysics and star formation efficiency. For planets, the same gradients alter upper atmosphere chemistry and the penetration depth of secondary particle showers. Over million-year windows these are subtle biases, over 100-million-year migrations they accumulate into distinct atmospheric histories. All the while, the black holes spiral together. Dynamical friction drags each hole through a sea of stars and gas until they bind, further hardening eject stars on intersecting orbits, scouring a core. In gas-rich cases, circumbinary disks take over the torque ledger, and the pair coalesces. The gravitational wave flash is brief but carries linear momentum. The remnant hole recoils, sometimes fast enough to wander from the center for a while, shaking the nucleus and modulating accretion. In a deep sense, even the metric that planets inhabit, the gentle curvature they never feel directly, is rewritten in the center, and the galaxy's future feedback budget changes with it. From the first tidal nudge to the final coalescence, the timeline runs from a few 100 million to a couple of billion years, long enough for multiple biospheres to rise and fall in the crossfire, short enough to keep the scars coherent in starlight that telescopes can map. Numerical experiments, n-body gravity married to hydrodynamics, reproduce the bridges, shells, and starbursts we see, and they show that small initial differences matter: mass ratio, gas fraction, orbital inclination, pericenter distance, halo concentration. Swap any of these and the migration map of stars changes, the corridors of high radiation, the lanes of frequent cloud crossings, the birthplaces of new disks. In the mind's eye it is easy to draw two colliding galaxies and a single star's luminous trail, a ribbon sprinkled with dust where its planets surf. Behind that single path lies a phase space ocean of possibilities. A merger is not only the death of two spirals and the birth of an elliptical, it is the rearrangement of habitable time across 1 trillion future orbits, a redrafting of where warm seas can persist and where skies are scoured into rust-colored storms. From the telescope's point of view the proof is stacked across wavelengths. In optical light the antennae and the mice display the archetypal bridges and tails. In the infrared, dust lanes glow where shocks compact cold gas. In radio, CO and HI arcs trace the inflows along bars. In X-rays, superwinds vent from starburst cores as hot, 10 million degree chimneys. At higher redshift, where the universe was younger and mergers more common, clumpy disks caught by JWST show the same playbook at cosmic noon: enhanced pair fractions, swollen star formation rates, and compact luminous nuclei that hint at black holes being fed. The morphology is different every time because the initial conditions are different every time: mass ratios, spin alignments, gas fractions, halo concentrations, but the ecological lesson for worlds is the same: the galactic environment is not a constant, it is weather, and mergers are its seasonal storms. Along the tidal tails, star clusters condense by the thousands. Some are super-star clusters with pressures and densities high enough to survive for a Hubble time. Tomorrow's globulars are being forged in the wreckage. Patches of gas in the far reaches of a tail can even assemble into self-gravitating islands, tidal dwarf galaxies, rich in heavy elements yet relatively poor in dark matter. If these dwarfs keep their gas and calm their turbulence, they will form new stars with planet-forming disks whose initial chemistry is already metal-blessed. Planetary systems born there will be children of a second draft, inheriting iron and carbon that previous generations minted and the merger dispersed. For planets already alive inside the drama, the first-order threats are atmospheric. A system migrating inward sees its magnetosphere compressed by a denser, faster wind and an edgier cosmic ray bath, ion pickup at the exobase eats at light constituents, and ultraviolet line radiation photodissociates water, pushing hydrogen to escape. Nitrogen can be sputtered from the top of the atmosphere. Ozone layers that once tolerated a quiet UV background can thin, shifting surface chemistry and ultraviolet safety margins. Under sufficiently harsh flux a thin, Mercury-style exosphere can blossom into a comet-like tail of sodium and potassium that streams downwind. Your silhouette planet, edged by a hairline atmosphere, would literally grow a luminous wake in the new radiation field. Nightside auroras widen and brighten as currents close through the ionosphere. Climate models would predict unfamiliar seasons, not because the star changed, but because the galaxy did. If the system's new route crosses the dense lanes near the inner kiloparsec, close encounters with giant molecular clouds become common. Each flyby perturbs the Oort cloud and the distant fringes of any wide planetary orbits. The statistics favor a ratcheting of long-period comet injections toward the inner system. Bombardment spikes follow with their double-edged consequences. Transient cooling from dust veils lofted by impacts, chemistry rewired by nitrate rain, oceans stirred by tsunamis, biospheres stressed and sometimes reset. A star kicked outward into the flaring outskirts experiences the opposite: fewer cloud encounters, a thinner cosmic ray fog, quieter bombardment, dimmer integrated starlight from the plane, longer, steadier epochs where slow geology outcompetes fast catastrophes. Stellar densities rise in merger-thickened bulges, and with them the rate of disruptive flybys. Wide planets, Neptunes and Jupiters on tens to hundreds of AU orbits, are the first to be shaken loose, leaving behind tightened inner systems and a halo of cold wanderers. Near the center, the two supermassive black holes sink, bind, and harden, three-body slingshots with the binary eject stars at hypervelocities. A fraction of their planets remain leashed to their fleeing suns, a smaller fraction are cut adrift as rogues, worlds without daybreaks traveling between galaxies. The rest of the galaxy feels the black hole's courtship indirectly, a scoured, low-density core, a flickering accretion diet, and, in the final coalescence, a gravitational wave kick that can briefly displace the remnant hole, jostling the nucleus and modulating feedback. Gas flows write the climatic ledger for the remnant. In a gas-rich major merger, torques cascade from kiloparsecs to parsecs, bars within bars, delivering fuel to the circumnuclear ring, inflating an AGN that bathes thousands of light-years in hard light. After the blaze, energy and momentum dumped into the circumgalactic medium can throttle new accretion, shock-heating the halo and quenching the supply of cold inflow. If quenching holds, star formation dries up and the remnant reddens into an elliptical with a hot X-ray corona. Habitable sky grows darker, comet traffic thins, extremes soften. If, instead, rainback from tails and fresh filaments persist, a new disk regrows inside the old spheroid. Metallicity gradients flatten, angular momentum is rebuilt and a fresh galactic habitable zone emerges, shifted outward, richer in solids, threaded by a thicker magnetic fabric. Simulations reproduce this arc because they resolve the crucial hierarchies: collisionless n-body dynamics for stars and dark matter, hydrodynamics for gas with radiative cooling and heating, prescriptions for star formation that depend on local density, turbulence, and self-gravity, feedback from supernovae, stellar winds, radiation pressure, and accreting black holes, non-ideal magnetohydrodynamics that tracks field amplification and reconnection. Change the mass ratio from 1 to 1 to 1 to 3 and you delay the starburst, tilt the disks out of the orbital plane and you spawn taller tidal plumes, raise the gas fraction and the remnant is more likely to regrow a disk. In every variant, the orbits of stars are scrambled over tens of thousands of light-years, and with them the climates of the planets they carry. Time is the last parameter that matters. A full merger, from first touch to relaxed remnant, stretches from a few hundred million to more than a billion years, long enough for a biosphere to adapt in steps, short enough that the scars still line up when we map them. A single star's path, rendered as a luminous spline through dust, could be followed like a traveler's log: calm arm, shocked ridge, quiet tail, crowded ring, hot wind, dark halo, new disk. Along that track, atmospheres are etched and replenished, bombardments surge and fade, chemistries pivot, and oceans either endure or are driven into red, dust-laden tempests. A merger is galactic plate tectonics on a cosmological canvas, and migration is the conveyor belt that moves whole worlds from one climate to another, not once, but again and again, until the remnant forgets the choreography and settles into its new face, while the planets remember every mile. Seen from the migrating star's deck, the galaxy's seasons change in slow motion. The integrated glow of the sky brightens as the orbit decays toward the crowded lanes, then dims as the star drifts outward on a trade of angular momentum. The constellations shear over millions of years as streaming motions rephase the background. The galactic habitable zone, the broad annulus where radiation, metallicity, and cloud encounters balance into long stable eras, does not stand still during a merger. It buckles, stretches, and folds like an isotherm on a weather map. Worlds ride across its contours. A planet that began slightly inside the annulus may find respite as the annulus expands under post-starburst quenching, another that started in a quiet ring can be swept across a seam where supernova rates jump. Habitability, once a radial statistic, becomes a trajectory-dependent story written by tides. Radiation budgets adjust not only in magnitude but in spectrum. Merger-driven starbursts harden the ultraviolet field while pumping the far infrared from embedded clusters. AGN phases add soft and hard X-rays that probe deep into atmospheres and crusts. Cosmic ray energy density rises with the supernova rate and the strength of galactic winds. Secondary particles drill chemistry in the middle atmosphere, forging nitrates and shifting redox balances in oceans. Magnetic draping around cold clouds channels these particles into filaments, so that a planet's long migration may traverse alternating bright and dim ribbons of ionization. Over tens of millions of years this paints different photochemical ceilings for methane and oxygen, reweights greenhouse balances, and toggles haze formation that can warm or cool by a few crucial degrees. Dynamical friction and torques map out the odyssey for the star itself. Each pericenter passage through a lopsided potential steals a little angular momentum, while resonant couplings with the bar exchange energy in packets that lengthen radial excursions. Vertical heating lifts the orbit above the plane. There, dust extinction drops but exposure to the diffuse ionizing field and halo cosmic rays rises. The Oort cloud breathes with each plane crossing, stirred by disk tides and brushed by passing clouds, so that bombardment risk is periodic on top of the slower merger cycle. For inner planets, the threats are cumulative rather than catastrophic, gentle but relentless ultraviolet that erodes high atmospheres, a cadence of weak, frequent impacts that bias evolution without erasing it, subtle shifts in cloud cover as ionization seeds aerosols that adjust planetary albedo. Chemistry in the interstellar medium, the pantry for future worlds, is remixed. Before the collision, metallicity declines with radius and differs from galaxy to galaxy. During the encounter, gas flows flatten those gradients. Enriched inner gas is flung outward in tails and fountains, pristine outer gas rains inward, shocks and turbulence homogenize pockets that were once segregated by shear. When the remnant cools, disks that regrow in this stirred medium offer protoplanetary disks with heavier element budgets farther from the center than their progenitors ever could. Rocky worlds become easier to forge at larger radii, volatile inventories are redistributed, iron cores, silicate mantles, and carbon chemistry all inherit the merger's mixing. Even the dust size spectrum is reset as shattering and coagulation in shocks retune opacities that will later set disk temperatures and snowline locations. Morphology writes constraints into the sky that observers can read. Long, kinematically cold streams preserve phase-wrapped signatures that betray when and how orbits were pulled apart. Shells and ripples map the epicenters of radialized stars. Thick disks with flares and boxy/peanut bulges betray bars that once funneled gas inward. Hot X-ray halos testify to feedback and virial shocks that shut down cold flows. In radio, synchrotron arcs trace cosmic ray highways along amplified magnetic fields. In millimeter light, CO ladders reveal dense flows sliding down ovals within ovals. To find the silhouette planet with a razor-thin atmosphere, you would look for sodium and potassium tails in transmission at twilight, for auroral oxygen on the night side, for erratic Lyman alpha as the exosphere breathes with the wind, all hallmarks of a world whose star has wandered into a new radiation regime that it did not evolve under. At the center of the drama, feedback sculpts the timeline. Starburst-driven superwinds punch out along minor axes, venting metals into the halo and beyond. If the halo is massive, those metals can rain back later, seeding second-generation disks. AGN jets and radiation pressure fountains shake and lift the inner gas, quenching or merely delaying the next round of star formation depending on duty cycle and geometry. When feedback is sustained and the halo shock heats fresh infall, morphological quenching follows. Even if some gas survives, the remnant spheroidal potential stabilizes it against collapse, raising tumor Q and starving new stars. If feedback is bursty and the mass ratio was modest, the remnant dodges total shutdown, tails fall back, a cool disk grows inside a red cocoon, and star formation resumes at a tempered pace. A planet's climate graph would register the difference as the long fade of irradiation extremes versus a sawtooth of on-off starburst epochs. The fate of wide planets and loosely bound debris depends on crowding. In thickened bulges and nuclear clusters, close stellar flybys pump eccentricities and inclinations, whittle away at outer planets, and churn comet reservoirs. A fraction of planets are traded in weak encounters or ionized directly from their stars, joining the census of rogues that drift between systems and sometimes between galaxies. Others remain loyal to their suns but are swept into the intracluster medium when the remnant later falls into a group. There they orbit in the diffuse light, bathing under a perpetual, dim city glow of all the cluster's stars. In these liminal environments, day length never changes because there is no sunrise, but the galactic weather still blows, slow plasma winds, sporadic particle storms from distant bursts, and the quiet rain of dust. On the largest scales, the merger's context matters. At cosmic noon, when gas fractions were high, a typical major merger would ignite more extreme starbursts and feed black holes more readily than a present-day analog. Planets then would have faced shorter, sharper radiation epochs and faster chemical enrichment. In the modern universe, dry mergers between quenched, gas-poor galaxies mostly stir stars and thicken envelopes. Their planets migrate without much change in the radiation field but with heightened risk of dynamical encounters in the dense cores. Minor mergers are numerically dominant, each is a gentler edit, a small torque here, a cloud crossing there, but the sum over many is a significant rewrite of a star's phase space address. Simulations turn these narratives into maps. In controlled experiments, change one parameter at a time and watch world's climates respond statistically. Increase the gas fraction, the starburst lasts longer, tails are denser, and the probability distribution for comet showers gains a fatter tail. Tilt one disk by 45 degrees, vertical heating grows, raising the mean cosmic ray flux on orbits that spend more time above the plane. Set the pericenter small, angular momentum loss is stronger, more stars are funneled toward the nucleus, and a larger share of planets see AGN-era skies. Merge in a live group, ram pressure trims tails early, reducing rain back, and the remnant quenches sooner, lowering late-time radiation but also starving future planet formation. The maps look like climate atlases, but instead of isobars and ocean currents they chart tidal torques, supernova densities, AGN duty cycles, and cloud encounter rates. For the imagined visual, a pair of galaxies interlocking, a single star's path painted as a glowing thread with dust sparkling along its wake, and beside it the fine line of a planet's atmosphere. It is accurate in spirit. The star's trajectory really does curl and widen through a sequence of potentials, and the planet's exosphere really can trail like a comet under harsher light. In some chapters the wake is bright, ionized by hard photons, in others it is nearly invisible, a tenuous breath held in a calmer wind. The scene is not a snapshot but a scroll, bridges stretching, knots of newborn clusters lighting and fading, the central engine flaring and idling, the dust lanes reweaving like rivers on a floodplain. Read end to end, the scroll explains why galaxy mergers are migration engines for worlds, not just for stars, cartographers of climates across kiloparsecs, editors of atmospheres, and authors of the long pauses and sudden accents in the biographies of oceans. And when the dance is finally over and the remnant relaxes, pressure-supported stars humming in triaxial symmetry, a hot halo holding court, perhaps a young disk regrowing within, the consequences continue to echo. The mixed metals and redistributed angular momentum set the stage for the next billion years of planet formation. The diaspora of streams and shells keeps feeding the outskirts with quietly falling stars. The central black hole, fed and merged, sets a new baseline for feedback. For any surviving civilization that watched the collision unfold, the night sky has been permanently edited. Constellations are strangers, the Milky River in the sky thicker or thinner, the faint aurora broader, the meteor calendar rewritten. They would know, in the most literal, lived sense, that galaxies do not merely collide, they migrate their worlds, and by doing so they change what is possible under every future sky. A merger also rewrites the rhythms of timekeeping that planets quietly obey. Milankovitch-like cycles of insolation that owe to orbital precession around the host star are unchanged, but the slow modulation from the galactic tide is not. As the stellar orbit thickens and tilts, the disk gravity that squeezes comet reservoirs breathes at a new cadence, the period of vertical oscillation lengthens, the amplitude grows, and long climate envelopes shift. Inward migration into starburst zones raises the floor of background UV and hardens it, pressing atmospheric photochemistry toward regimes where hydrogen escape outruns replenishment and nitrogen oxides accumulate. Outward migration cools the background and lengthens radiative relaxation times in stratospheres, biasing cloud microphysics toward high, thin hazes that brighten the planet and subtly trim the greenhouse. None of this flips a temperate world into a runaway in a single epoch. Instead, the merger adds a galactic metronome that nudges climate attractors over tens of millions of years. Magnetism is the planetary shield that either holds or frays under this new sky. A dynamo powered by rotation and internal heat can swell its magnetopause to fend off a denser wind, but if migration drags the system through regions where the galactic magnetic field is tangled and strong, reconnection events become frequent and violent. Each episode dumps energy into the upper atmosphere, widening auroral ovals and catalyzing chemistry that eats at ozone and crafts nitrates and peroxides. For moons around giant planets, the story is doubled, magnetospheres inside magnetospheres, with currents braided through plasma tori that brighten under higher ionization. Many exomoons would meet their first real winters not from distance to their star but from a merger-forged increase in charged particle rain. Tidal heating, too, gains a new role. Closed stellar flybys and thickened bulges pump eccentricities in wide-orbit giants, resonances shuffle inner architectures. A moon that was once tidally quiet can be driven into a flexing regime where interior oceans thaw or volcanoes awaken. Inward drifted systems that brush the circumnuclear ring feel a different tide altogether. The changing non-axisymmetric galactic potential itself adds a slow, global squeeze and release that a planet will only ever register through rearrangements of comet influx and dust deposition. The net result is a planetography written in faint strokes, extra layers in polar ice, sporadic deposits of micrometeoric iron, a bias in volcanic degassing as mantle oxidation state reacts to that trickle of delivered metals. The stellar neighborhoods along the way become diverse classrooms. In a bridge between galaxies, the density is low and the nights are black except for the ribbon of the tail, radiation is mild, but passages through shocked knots are abrupt, like storms after long calms. In a nuclear ring, the sky is crowded with young clusters that rise and fade within a few 100 million years, and the background is as bright as a permanent aurora. In a regrown inner disk, the pattern is ordered again, spirals, resonances, and gas lanes restored, but the chemistry is different, metals more evenly mixed, dust size distributions retuned by earlier shocks, snowlines shifted outward for newborn protoplanetary disks. Planets that will form here will tend to be rocky farther from their stars, icy giants richer in heavy elements, and moons more plentiful because solids were abundant where subnebulae cooled. Observationally, the planets that live through these migrations would betray their paths in small, compound ways. Transmission spectra with sodium and potassium wings that thicken only when the host star is embedded in a dusty lane, variable Lyman alpha that responds to wind pressure changes on thousand-year cycles, radio-auroral lines that brighten as cosmic ray density rises downstream of superbubbles, thermal phase curves with a new asymmetry as high-altitude hazes scatter more strongly in forward directions under a hardened UV field. No single signature proves a merger-driven migration, but together they compose a dossier a patient observatory could build. The world's climate is being steered by a sky that isn't constant. On the stellar side, the kinematics of survivors keep score. A planet-bearing G star that began life on a near-circular, thin disk orbit may end on a rosette with apocenter in a shell and pericenter skimming a boxy bulge, its action angle coordinates misfit for any quiet galaxy. The open cluster it was born with will have long since phase mixed, but the remnant carries clumps in velocity space, fossils of resonant passages and tidal wraps. In those clumps live siblings whose planets experienced similar radiation histories. A comparative planetology across such groups would find matching epochs of bombardment and shared atmospheric chemistries out of proportion to age or stellar type alone. Zoom out to the cosmological setting and the statistics come into focus. Major mergers were common when the universe was a few billion years old, minor ones are common now. Gas-rich collisions sculpted intense, brief episodes when the galactic habitable zone was a moving target, darting inward and outward as starbursts lit and faded. Gas-poor encounters mostly rearrange stars. They migrate worlds without dramatically changing the radiation sea, yet they elevate the rate of close encounters in the core and trim the outer architecture of planetary systems. Group environments add intruders, ram pressure from the intragroup medium strips tails early, throttles rain back, and hastens quenching, which dims the long-term radiation but also reduces the feedstock for future disks. A planet's biography is therefore a function of merger mass ratio, gas fraction, orbital geometry, and the larger halo it all unfolds within. The endgames are varied. Some remnants quench and stay quiet, their hot halos preventing fresh cold inflow. Planets inside enjoy long, stable millennia punctuated only by the slow grind of geology. Others rejuvenate, tails fall back, filaments reignite, a crisp blue disk spins inside a red cocoon, and the galactic habitable zone stabilizes in a broader, more metal-rich band. A few become way stations in a larger hierarchy, falling into clusters where intracluster light is the permanent twilight and the biggest black holes keep the gas too hot to condense. In all cases the merger has redistributed possibility, where rocky planets can form, how often bombardments arrive, how hard the sky shines, and how strong the winds breathe at the edge of air. If we place our own future in this frame, the eventual meeting of our spiral with our neighbor reads less like doom and more like itinerary. The solar system is unlikely to be torn from the sun by galactic tides, but its orbit will be traded and thickened, the outer architecture will be stirred, and the background sky will brighten and dim in chapters as we pass through lanes and rings. Depending on phase and geometry, the sun could spend epochs in a regrown disk or loiter in a puffed-up halo. Over those times, climates on any surviving worlds will follow the slow choreography we have traced, gently rising particle baths, sporadic comet showers, altered high clouds, a different auroral song. Oceans will not boil because galaxies kiss, they will struggle or thrive because migration drags their planets through new neighborhoods with new rules. For your visual, two galaxies in the act, a single star inscribing a glowing trail, a planet's atmosphere drawn as a razor line with a faint, sodium-bright tail, there is one more detail worth adding. In the dust around the trail, new stars are kindling from gas the merger compressed, in the wake of the planet, grains lofted by micrometeorites glint as a ghostly fan. Far behind, shells ripple where the potential has rung, and ahead, the central engine flickers. The path is not just a record of where the star has been, it is also a draft of where worlds will emerge next, richer in metals, different in weather, set to orbit under a sky whose brightness and color were mixed by the same tides that braided that path. A merger is an editor of futures. Migration is its pen. Interacting galaxies do not only stir stars and gas, they shuffle archives and open exchange routes. When tidal tails thread through a group, they act as highways for debris, ice-rich shards from disrupted dwarf galaxies, metal-heavy splinters from compact starburst cores, dust clumps shocked into centimeter pebbles. The flux of interstellar visitors rises. Elongated, outgas-scarred bodies cross planetary orbits more often, some captured into temporary loops before escaping back to the tide. Each close pass is a lesson in alien chemistry, Each impact is a small edit to crusts and atmospheres. Where tails brush the circumgalactic medium, shear and ram pressure peel gas into ribbon wakes, and in the wake star clusters ignite that will one day look like ancient globulars, their stars alpha-enhanced and tightly bound, their internal dynamics a fossil of the pressure cooker birthplaces that mergers provide. Clusters and groups change the syllabus again. A galaxy preprocessed by companions arrives at the main collision already gas poor. Harassment and tidal stirring have thickened its disk and heated its stars. When the final embrace begins, ram pressure from the intracluster medium scours what gas remains, carving jellyfish filaments that sparkle with H2 knots and young clusters. Planets circling stars embedded in these stripped heads see two winds at once, the local blast from newborn massive stars and the headwind from the cluster's plasma. Bow shocks form at magnetopauses, exospheres draw out into long, faint sodium tails that would paint the nights of any skywatchers there with a quiet, coppery glow. Further in, brightest cluster galaxies drink the rain of stripped gas and starlight, their radio lobes inflating caverns in X-ray hot halos. Feedback from those giants sets the thermostat that decides whether future disks can condense or whether the whole environment stays quiescent and dim for a Hubble time. Where black holes are concerned, the ledger of energies widens. Dual active nuclei flicker as gas sloshes into both cores. When they bind, circumbinary disks carve gaps and launch periodic outflows. Tidal disruption events spike as stellar orbits are scrambled near the pair. For a few million years the nucleus is a graveyard light show of shredded stars and thermal ashes. When the holes finally coalesce, anisotropic gravitational waves kick the remnant, off-nuclear AGN wander through the inner kiloparsec, lighting dust lanes and shocking circumnuclear rings. This shuffling modulates the hard photon climate for any stars whose migrated orbits thread the inner few hundred parsecs, writing a chapter of intermittent high-energy seasons into their atmospheric histories. Star formation in mergers is not just more, it is different. Pressures jump by orders of magnitude in clumps where turbulence and self-gravity meet. The initial mass function may tilt slightly top-heavy, briefly boosting the population of massive stars that explode quickly and seed the medium with oxygen and silicon. Radiation pressure, winds, and supernova shells overlap to make superbubbles stitched by magnetic fields. Cosmic rays are accelerated in their shocks and thread outward along ordered lines amplified by shear. For planets, the net is a harder spectral diet and a higher ionization rate in the upper atmosphere. For protoplanetary disks born in this bustle, ionization raises magnetic coupling, stoking instabilities that regulate accretion and reshaping where snowlines sit. Because shocks shatter grains while dense pockets coagulate them, the grain size distribution resets, opacities change, mid-plane temperatures shift, planetesimal formation zones migrate. A remnant that regrows a disk will therefore mint its next generation of planets along contours that did not exist before the collision. Kinematics carry the memory long after the fireworks fade. Phase-wrapped shells record the timing of minor mergers. Thin, kinematically cold streams curve around the remnant like pale handwriting. Boxy/peanut bulges mark the bars that once funneled gas. Chemical tagging binds this map to chemistry. Stars in a given tidal wrap share abundance fingerprints, iron, alpha elements, S-process tracers, that shout their common past. A civilization patient enough to build a Gaia-class census could read its galaxy's migration history like dendrochronology, then cross-match climates on its worlds to epochs when its sun crossed dense lanes, shells, or rings. It would learn that habitability is path-dependent because the galaxy's potential is a moving landscape, and that, where a planet is cannot be separated from when its star's orbit dragged it through a brighter or darker sky. Not every collision ends in a red, quiescent spheroid. Gas-rich, low-mass halos can miss full quenching, tails rain back, bars regrow, and a blue disk spins within a warm envelope. Angular momentum is not destroyed, it is redistributed, sometimes rebuilt by fresh inflows along cosmic filaments that the merger reorients. In those cases the galactic habitable zone settles into a broader, more metal-rich annulus than before, with fewer violent episodes and a gentler background after the starburst ages. Elsewhere, in the deep wells of clusters, cooling flows try to condense and are throttled by radio mode feedback. keeping the big galaxies dim and their skies austere. Planets there migrate mostly through changes in crowding and encounter rate, their radiation climate is steady, their dynamical environment restless. Minor encounters, the ones that never make the postcards, accumulate. Each 110 or 120 merger is a small torque that shifts guiding centers by a few kiloparsecs, thickens orbits, spawns a warp, or tips the disk. 1,000 such edits across a few gigayears imitate a major event's broad effects, redistributed metallicity, altered cloud encounter statistics, a different bombardment cadence. Many stars that never see the core of a major merger still walk away with rewritten addresses, and their planets with revised climate baselines and impact calendars. In dwarfs, the stakes change again, low metallicity trims dust and coolants, favoring bursty star formation, long gamma-ray bursts are rarer in metal-rich giants and more common in such dwarfs. When dwarfs participate in a larger merger, their brief, hard outbursts punctuate the regional sky with collimated danger cones that a few unlucky worlds will face. From an exoplanet observer's angle, the fingerprints are cumulative and multi-wavelength. Far UV and X-ray monitoring would catch stepwise changes tied to passages through star-forming lanes. Radio observations could time auroral maser brightenings as cosmic ray density fluctuates. Transmission spectroscopy near sodium and potassium doublets would reveal exospheric breathing under stronger winds. Submillimeter maps of CO and C2 would place the host star relative to inflow streams and shocked ridges. Precision astrometry would show the host's action angle drift as the potential evolves. Even gravitational waves join the dossier. A Lisa band background from supermassive black hole pairs sketches the recent merger rate, a kind of barometer for how often the galactic climate flips into starburst or AGN seasons and thus how often planetary atmospheres in that universe are put under stress. There is also trade across systems. When wide binaries are ionized by flybys in a thickened bulge, liberated planets can be exchanged. Capture cross-sections are tiny, but in billion-year tallies they are not zero. Rogue worlds pass through tails and bridges and, if lucky, graze a star's hill sphere at just the right speed to be caught. Such captures would be rare trophies, a methane giant with isotopes whispering of a different nursery, a super-Earth whose rock chemistry mismatches the star it now circles. Mergers turn the galaxy into a slow market where a few goods change hands, and in those exchanges the diversity of worlds multiplies. All of this writes back into biology wherever it exists. A slowly hardening UV background pressures photosynthetic pigments to shift windows, a higher ionization rate enriches nitrates delivered by rain and lightning, nudging nutrient cycles, a heavier bombardment tail favors subterranean or submarine refugia and encourages evolutionary experiments in radiation repair. None of these guarantees extinction or renaissance, they reweight the dice. Over 10, 100, 500 million years, the accumulation of small nudges defines whether oceans keep their clouds, whether continents breathe CO2 in familiar rhythms, whether the aurora is a polar ribbon or a planet-wide veil. And still the picture is wider. The stars scattered into intergalactic space by the three-body pinball around the central black hole binary carry with them globular clusters, ultra-compact dwarfs, and stripped nuclei, dense relics that can host intermediate-mass black holes and nuclear star clusters. Their tidal fields shear any long-period comets and sculpt intra-cluster dust. Their occasional flares add quiet punctuation to a sky otherwise lit only by the diffuse glow of the cluster. Some of their planets remain bound, adrift in the dim between fields night. Some become rogues, slowly freezing from the top down, kept barely warm by radiogenic decay and tidal flexing if they bear moons. Even in exile, the merger's migration writes a possible ecology. Geothermal lakes beneath ice, chemistry powered by gradients that ignore the absent sun. When the remnant finally finds its new equilibrium, the violent relaxation is over but the memory persists in orbits and elements. The day-to-day sky becomes reliable again, the long storms of starburst and AGN weather recede, the background settles. Yet the map has changed, metallicity is flatter, angular momentum has been reapportioned, the hot halo's entropy has been lifted, and the ledger of streams and shells continues to settle its accounts as they fall back. For worlds that endured, the story reads like a pilgrimage, the same star, the same gravity at home, but a path through space that altered the color and pressure of the sky, the pace of impacts, the chemistry of air and sea, and the probabilities of life's gambits. If you trace the luminous thread of our imagined star across the merger's canvas and keep the silhouette of its planet always beside it, you can watch climates, chemistries, and chances evolve in step with that line. Migration is not an epilogue to the collision, it is the experience of it, measured not in orbits lost and gained but in the biographies of worlds. Open clusters live and die faster inside a merger, and that accelerates the classroom where planetary systems are schooled. Newly formed clusters in shocked ridges start compact and massive. Within a few 100 million years, tidal heating and passages through dense lanes peel off members. While the cluster is still bound, close flybys are common enough to trim the widest planets and pump eccentricities in the survivors. When the cluster dissolves, its stars carry correlated velocities, kinematic graffiti that persists long after the last gas has blown out. Planets born around these stars inherit that dynamical prehistory, a slightly hotter distribution of eccentricities, a higher fraction of misaligned spins from disk warps driven by the early environment, and a population of moons and rings sculpted by stronger tidal histories. Shock fronts where streams collide are more than star formation triggers, they are foundries for solids. Grain collisions shatter and sinter dust, centimeter pebbles concentrate in pressure bumps, and local enhancements of short-lived radionuclides from nearby massive stars tweak early thermal budgets in planetesimals. In a calm disk, snowlines sit where starlight sets the temperature. In a merger, the background far-infrared glow and intermittent UV flares shift those lines outward and back, seasoning protoplanetary chemistry with a variability absent in quiet spirals. The outcome is a broader radial swath where rocky cores can form, a heavier enrichment of giant planet envelopes, and a higher odds of moons because solids are plentiful where circumplanetary disks cool. Dark matter sets the stage and keeps score. The halos of the two galaxies interpenetrate first, trading orbital energy through dynamical friction. Subhalos stir tidal heating in the outskirts, raising the chance that cold streams fragment into star-forming knots. As the baryons torque and radiate, the halo responds adiabatically in some regions and impulsively in others, changing the frequencies that stars feel as they orbit. In action, angle language, resonances sweep through phase space like combs. Stars that land in those teeth migrate most, and it is along their paths that planets see the largest environmental swings. Subhalos that survive the crossing can later trigger ripples in the regrown disk, refreshing spiral structure and keeping cloud encounters above the background for gigayears. The central black holes run a parallel story in slow motion. Dual AGN duty cycles stitch hard photon seasons into the inner kiloparsec. Circumbinary disks launch periodic winds that comb dust lanes, tidal disruption events spike briefly and then fade. The final coalescence produces a recoil that can displace the whole by tens to thousands of parsecs, briefly off-centering the nucleus. For planets on migrated orbits that thread the inner few hundred parsecs, this is not an immediate existential threat, it is a change in long-term weather, X-ray baths that flicker, ionization fronts that advance and retreat, and a rearranged pattern of hot chimneys venting superwinds. Habitability under these skies becomes a stack of probability distributions rather than a single yes/no annulus. Background UV sets the pace of hydrogen escape and photochemical shielding, cosmic ray density sets the rate of nitrate production and mutagenesis, cloud encounter statistics set the cadence of bombardment spikes, stellar crowding sets the cross-section for disruptive flybys. Shift anyone and the mean moves, shift all at once, as a merger does, and the variance grows. Biospheres robust to noise, thick atmospheres, magnetic dynamos, deep oceans, metabolic flexibility, are favored. Photosynthetic pigments may drift to redder or bluer windows as the spectral diet hardens or softens, nitrogen cycles accelerate under higher ionization, near-surface life retreats poleward or downward during starburst chapters and rebounds in the lulls. The geologic record on such worlds would read the merger in fine print. Spallation isotopes in ice or carbonate, beryllium-10, chlorine-36, would wax and wane with cosmic ray flux. Platinum group layers from impactors would stack in clusters rather than Poisson rain. Volcanic outgassing patterns would show subtle biases if oxidation states shift with delivered dust and metal micrometeorites. Even paleomagnetism might carry the signature of more frequent magnetic storms, rapid excursions recorded alongside nitrate-rich layers that signal solar-independent particle rain. Rogue worlds and captured strays broaden the catalog. Hypervelocity stars ejected by three-body dances around the sinking black hole binary sometimes keep a planet, most don't. Freed planets drift through tidal bridges and halos, cooling until their oceans, if any, move beneath ice, sustained by radiogenic and tidal heat. Capture is rare but not zero. A super-Earth with chemistry mismatched to its new host star's abundance ratios would be a telltale trophy of exchange. In tidal dwarf galaxies, born metal-rich from recycled gas yet poor in dark matter, planet formation proceeds in compact, slowly rising rotation curves and shallow potential wells. Wide, fragile planetary architectures would be unusually vulnerable to even modest flybys, yet their rocks would start chemically mature. Technosignatures, if they exist, would adapt to the merger's metronome. Civilizations under a rising particle bath could bury power grids, inflate magnetic shields, and shift agriculture beneath polarized glass that filters the hardening UV. Radio leakage would flicker with auroral storms. City light spectra could show engineered aerosols tuned to restore lost shielding. During AGN chapters, night glow would brighten and communication strategies would pivot to frequencies that scatter less in ionized gas. A deep-time survey of such signals would find not randomness but correlation with the galaxy's own seasons: brighter, harder skies, dimmer, softer epochs, long interludes of quiet when the remnant finally relaxes. Our local parable is Milky Way, Andromeda. On present estimates, the first close pass lands in a few billion years, with full coalescence stretching across roughly another billion. The Sun is unlikely to be stripped, but its guiding center will wander, the outer architecture will be stirred, Oort cloud comets will see their injection rate modulate, the background sky will at times grow busy with star-forming knots and at others thin into a gentle halo glow. The more decisive climate driver for Earth then will be stellar evolution, not the merger, but if humanity's descendants live elsewhere in the solar system or beyond, their weathers will ride the merger's tides in precisely the ways traced here: particle baths a little stronger, comet calendars a little less Poisson, auroras a little wider, starry nights rewritten. Observationally, the dossier a patient observatory could assemble on a single migrating world is rich. Astrometry pins the host star's drift through an evolving potential, millimeter maps place it relative to CO bright inflows and C2 shocks, X-ray and far UV light curves record starburst and AGN seasons, radio catches cyclotron masers from auroral caps, transmission spectra near Na-D, Ki, H-alpha, Hi108330A, and Li-alpha watch the exosphere breathe. Mid-IR phase curves measure haze episodes when photochemistry tips. Stack these against a model of the merger's timeline, and you infer not just the planet's climate but the chapters of the galaxy that wrote it. Even after the fireworks subside, the remnant keeps editing possibility. If quenching holds, the hot halo's entropy and the rebalanced angular momentum stabilize gas against collapse, morphological quenching, and the galaxy reddens into a long evening. Planets inside enjoy fewer violent seasons, bombardment tails thin, atmospheres find slow equilibria. If, instead, rainback and filaments feed a new disk, the annulus of relative safety broadens and moves outward in a more metal-rich medium. The next wave of planets forms with heavier cores, richer moons, denser rings, and perhaps a larger share of temperate super-Earths at radii that were previously too dust-poor. The merger does not choose winners, it shifts the odds. For the scene you're painting, two galaxies interlocking, a star's luminous spline marking its changing address, a planet's atmosphere etched as a needle-thin line with a faint sodium wake, you can add layers that are true to physics. Let the trail pass through a knotty, H2-beaded ridge where newborn clusters glow, show the circumnuclear ring as a bright, clumpy torus where the sky is a permanent dawn, fade into a quiet halo where the trail thins and the background is a dim city glow of integrated starlight. Dot the path with fine, intermittent fans of dust, micrometeoric veils after cloud crossings, and, just once, render a brief, pencil-thin jet from the nucleus in the distance, a reminder that black holes, too, keep time. In the end, a merger is not merely the arithmetic of two stellar populations and a ledger of angular momentum. It is a weather system written across a galaxy, a slow conveyor that migrates suns and drags their worlds through new radiation seas, new bombardment calendars, and new chemical stores. Planets survive, adapt, and sometimes thrive, not despite the collision, but through it, because the same forces that threaten also enrich, seed, and mix. Follow a single star's thread far enough and you watch climates and chances evolve with it. Zoom out and you see that countless threads together weave the remnant's future. The galaxies collide, the worlds migrate, the night sky, forever after, reads differently. In the late stages of a major merger, the physics simplifies and sharpens at once. The global potential smooths into a triaxial swell, violent relaxation finishes its shuffle, and the remnant stars settle into orbits set more by pressure than by rotation. Yet the baryons keep a double life. A hot, X-ray halo retains heat and entropy from past feedback, while cooled pockets, either rain back from tails or fresh filamentary inflow, pool into a new, rotating sheet inside the spheroid. Where that inner sheet forms, spiral structure reappears, bars reassert torque, and a second chance disk writes ordered lanes across a body that otherwise looks like an elliptical. For migrated planetary systems, this means a last environmental pivot, a return from the coarse-grained, crowded bulge to patterned traffic where cloud encounters and radiation fields vary more predictably with radius and arm phase. The chemistry of that reborn sheet carries the merger's memory. Metals are flatter with radius, carbon and oxygen more evenly shared, dust-to-gas ratios higher farther out than before. Snowlines in newborn disks sit at larger distances because opacities and midplane temperatures changed in the shattering and coagulation the merger forced. Rocky cores seed across a broader annulus, giant planets accrete with envelopes pre-seasoned by recycled metals, circumplanetary disks cool efficiently enough to mint large moons. If you compared these planets to their older cousins from the pre-merger era, you'd find denser cores, thicker moon systems, and ring architectures biased by a richer solids inventory. Migration thus edits not only climates of existing worlds but the blueprint of worlds yet to be. Even after the remnant calms, kinematic fossils keep speaking. Thin, cold streams thread the outskirts along which stars, and any planets they carry, spend gigayears in dim corridors largely free of clouds and shocks. Shells mark past radial plunges, their apicenters are quiet perches with long dynamical times and low encounter rates. Boxy/peanut bulges betray bars that funneled gas, stars inside show a higher frequency of eccentricity pumping and, for the widest planets, a larger attrition rate. Tie chemistry to motion, chemical tagging, and the map turns into a ledger, alpha-enhanced streams from early, bursty episodes, iron-rich wraps from later, calmer rainback. A patient civilization could cross-check climate histories on multiple worlds against that ledger and recover the sequence of passages, bright lanes, quiet halos, hot rings, that sculpted their skies. The radiation diet that planets swallow after a merger often has a long tail. Supernovae fade on tens of millions of years, but cosmic rays trapped in superbubbles leak slowly along ordered magnetic fields that mergers amplify. Those fields thread the regrown disk and halo, guiding particles into filaments that overlay the optical arms like invisible arteries. Over million-year windows the dose is modest, over 100 million-year windows it becomes a structural term in atmospheric chemistry. Methane ceilings, oxygen false positives, nitrate rain, and haze episodes will follow the slow breathing of these filaments, not merely the instantaneous star formation rate at the host star's address. For observers, that means biosignature interpretation must include the galaxy's recent weather, not just the planet's local star. Dynamics keep a few surprises in reserve near the center. In some remnants, the coalesced black hole recoils and oscillates through the inner bulge, displacing the ionizing lamp that set the hard background. Periodic off-nuclear AGN episodes light different dust lanes, altering where chimneys vent and where winds comb. For stars whose migrated orbits graze a few hundred parsecs of the core, these are long, intermittent seasons, gentle rises in X-ray and UV flux, higher ion pickup in exospheres, broader auroral ovals. None of it strips an Earth-like atmosphere in one chapter, but over the slow metronome of the remnant's relaxation it draws extra lines in the planetary stratigraphy, thin layers rich in cosmogenic isotopes, abrupt shifts in high-altitude aerosol loads, subtle steps in the redox budget of oceans. Minor mergers never stop, even after the headline event. Each 120 arrival tilts the disk a degree, thickens it a notch, seeds a warp, or refreshes spiral structure. Statistically, these are the nudges that keep cloud encounter rates and comet injection fractions above the quiescent baseline. A system that was lucky through the main collision may meet its harshest winter during a humble, late flyby that perturbs its Oort cloud while the larger galaxy appears placid. Conversely, a world punished during the starburst might enjoy tens of millions of years of serene skies once the remnant's bar weakens and the hot halo throttles fresh inflow. Habitability under these conditions becomes a distribution with fat tails, rare harsh decades in a generally mild climate, or rare long calms in an otherwise lively sky. Group and cluster environments extend the lesson. If the remnant falls into a cluster, intracluster plasma trims any fragile gas streams and dulls rain back, making quenching more durable. Intracluster light becomes the permanent twilight, ram pressure adds a slow, second wind to every magnetosphere. Jellyfish phases may recur in miniature as the remnant satellites are stripped, localized bursts in those tentacles add hard light in irregular patches. Planetary systems moving through this web see a demographic shift, fewer new protoplanetary disks, but the ones that form are metal-rich, fewer giant clouds, but the crowding in central galaxies keeps the flyby cross-section elevated. It is a different recipe for the same stew, radiation steadier, dynamics busier. On the scale of a single migrating star, the long logbook remains legible. The orbit warms and cools across the background as it trades angular momentum with bars and ovals, vertical oscillations lift it above dusty lanes, thin the extinction, and expose it to a softer but more pervasive ionizing field, pericenter passages through pattern speeds kick actions and phase angles in discrete packets. The Oort cloud breathes with each plane crossing, comet calendars cluster around those beats, spallation isotopes rise in sync with cosmic ray filaments pinned to old superbubble walls. None of these entries is dramatic alone. Together they amount to a climate written by a galaxy that learned a new rhythm when it merged. If technology arises under such a sky, its defensive imagination will rhyme across worlds. Power grids harden against geomagnetically induced currents, farms migrate under polarized canopies to blunt UV spikes, navigation constellations carry radiation counters to warn of particle weather set not by the host star but by the galaxy's heartbeat. Even art would change, auroras as seasonal festivals, sodium exospheric tails as calligraphy along the horizon, old constellations painted next to the new to remember the pre-merger sky. These are cultural fossils linked to astrophysical ones, proofs that migration is lived, not merely inferred. By the time the remnant is truly old, the drama is encoded in structure and chemistry rather than in light. The hot halo's entropy is high, cooling is rare, star formation ticks over at a whisper or not at all. Streams have mostly fallen in, shells have softened. The inner disk, if one regrew, is mature, its spiral contrast low but persistent, its bar slow. Planets that lasted this long inhabit the most predictable chapter they will ever know, steady particle baths, impact tails gone thin, photochemistry near equilibrium. Yet their rocks, ices, and atmospheres still carry layered signatures of pericenters and passages, AGN seasons and starburst chimneys, cloud crossings and quiet halos, an index of the migration written page by page across hundreds of millions of years. Return to the image of two galaxies entwined, a single star's luminous path crossing the canvas, a planet's hairline atmosphere sketching a faint, sodium-bright wake. Let that path traverse, in sequence, a shocked, H2-beaded ridge, a dark lane where dust swallows starlight but cosmic rays whisper through, a circumnuclear ring under a permanent dawn, a thin halo where the city glow of integrated starlight replaces constellations, and finally a young inner disk rebuilt from the wreckage. At each chapter, jot the small, cumulative edits, a percent more ultraviolet here, a few extra comet years there, a thicker haze, a wider aurora, a cooler, clearer winter. That ledger is the whole thesis. Galaxies collide, orbits are traded, worlds migrate into new environmental regimes. Habitability is not a circle drawn once around a star, it is a story braided with the galaxy's own, and mergers are the episodes that turn the page. Inward plunge orbits are captured by a transient bar and resonantly torqued toward the inner kiloparsec. Cloud encounters become frequent, the supernova rate in the neighborhood rises, and the stellar background hardens with a young, UV-bright population. Cosmic ray energy density tracks the starburst, then lags as particles leak out of superbubbles along amplified magnetic fields. Atmospheres on temperate planets respond first in the exosphere, hydrogen escape speeds up, helium 10,830 A absorption deepens, sodium and potassium lines sprout tenuous wings, then deeper down as photochemistry rebalances, ozone thins, and high, forward scattering hazes brighten the planet's morning and evening limbs. Impact statistics come in episodes, a few million years of comet showers after each dense lane crossing, then lulls. Wide giants are pruned by flybys in the thickened bulge, inner rocky worlds survive but collect a patchwork of isotope layers, beryllium 10, chlorine 36, that mark the particle weather like tree rings. If the core turns AGN bright, X-rays penetrate to tens of millibars, heating the middle atmosphere and enlarging the polar caps where auroral chemistry writes nitrates into snow. Outward fling orbits trade angular momentum the other way, surfing a tidal tail to epicenters tens of kiloparsecs from the original disk. Here the sky is dimmer, the cloud field sparse, and stellar crowding low, the price is exposure to a softer but more pervasive ionizing bath from the hot halo. Bombardment tails thin, cloud-driven resonances in the Oort cloud relax, and climates settle into long, steady baselines punctuated by rare, large impacts. Photochemistry cools toward methane-friendlier regimes, high clouds become optically thin veils that raise albedo just enough to matter. The main hazard is starvation, fewer fresh metals and dust to fertilize future disks, slower recycling of volatiles, a trickle economy of micrometeorites rather than the rich rain of the inner lanes. For civilizations, these are good centuries and good millennia, the particle weather is predictable, auroras are narrow, and astronomy enjoys a darker, cleaner sky. Lupin return orbits ride a tidal bridge, linger in the intergalactic corridor, then fall back through a shocked ring as the remnant reassembles. This itinerary stacks contrasts. In the bridge chapter, radiation is mild, but brief passages through H2 beaded knots deliver sharp UV flares. In the ring chapter, the background brightens to a permanent dawn, with compact clusters rising and fading in human history windows. Atmospheres learn to breathe, exospheres expand and contract with the wind pressure. He-10830A and Li-alpha line depths oscillate on KYR timescales, radio-auroral emission brightens when the star crosses old superbubble walls rich in ordered fields. Bombardment calendars acquire a bimodality, quiet centuries punctuated by short, dense storms. Under the hood, the machinery is the same across paths. Non-axisymmetric structure, bars, ovals, spiral modes, moves angular momentum by gravitational phase shifts, funneling gas inward, bars within bars, and throwing the outer disk into tails. Violent relaxation during the deepest passages stirs stellar energies without collisions, while blurring and churning, radial heating versus true guiding center shifts, reshape orbits on longer times. Vertical heating thickens the disk, action, angle resonances sweep phase space like moving combs. The two supermassive black holes sink by dynamical friction, bind, and harden, their loss cone appetite spikes the tidal disruption rate, their coalescence launches a recoil that can off-center the hard photon lamp for a few dynamical times. Feedback couples the scales, supernova-driven superbubbles and AGN jets raise the halo's entropy, throttle fresh inflow, and, if sustained, lock the remnant into morphological quenching where gas survives but resists collapse, tumor Q up, star formation down. The chemistry of the interstellar pantry is also remixed. Shocks flatten metallicity gradients by hurling enriched inner gas outward and dragging pristine outer gas inward, grain shattering and coagulation reset the dust size spectrum, ionization fronts from starbursts and AGN alter the CO/C balance that sets cooling. When a new disk grows inside the spheroid, snowlines sit farther out, opacity profiles change, and planetesimal birth zones widen. Expect denser rocky cores at larger radii, heavier giant planet envelopes, and circumplanetary disks that cool efficiently enough to build populous moon systems. Tidal dwarf galaxies forming in the tails start metal-rich despite shallow potential wells, so their planets will be chemically mature, yet dynamically fragile, wide orbits easy to perturb, architectures easily reshaped by even modest flybys. Observationally, a patient survey could diagnose a merger-migrated world by its compound dossier rather than any single smoking gun. Precision astrometry pins the host star's action drift through a changing potential. Millimeter maps place the star relative to CO bright inflows and C2 lit shocks. Far UV and soft X-ray light curves tag starburst chapters, occasional hard flares betray AGN seasons. Transmission spectra around Na-D, Ki, H-alpha, He10830A, and Li-alpha trace an exosphere that expands under stronger winds. Radio catches cyclotron masers from auroral caps whose power follows cosmic ray density more than stellar flares. Mid-IR phase curves register haze episodes when photochemistry tips. Stack these time series against a dynamical model of the merger, and the planet's climate becomes a solved inverse problem. Translate the same logic to our long-term itinerary. The Milky Way, Andromeda encounter will not peel Earth from the Sun, but it will thicken and tilt the solar orbit, brighten and dim the integrated sky in chapters, and modulate the Oort cloud injection rate. Earth's climate then will be dominated by solar evolution, yet for habitats elsewhere in the system, outer planet moons, subsurface seas, the merger's metronome will matter, charged particle rain rising modestly, auroras widening, micrometeorite gardening speeding or slowing with cloud crossings. In a regrown disk phase, a broader, more metal-rich galactic habitable annulus may emerge, easing the formation of rocky worlds around K-dwarfs at larger radii than today. If technology is there to watch, it can forecast galactic weather the way we forecast solar storms now. Magnetometer constellations report currents driven by reconnection with the ambient field. All sky UV monitors flag starburst windows, CO/C2, tomography maps inflow lanes years to decades before a system crosses them, Lisa-band gravitational wave alerts mark the late dance of nuclear black holes, a preface to possible off-nuclear AGN seasons. Engineering follows suit, power grids hardened against geomagnetically induced currents, agriculture shaded with polarization-tuned glass to blunt hardening UV, spacecraft trajectories that dodge enhanced micrometeoroid streams predicted from upcoming cloud passages. The deep claim hidden in all this detail is that habitability is not simply a radial annulus around a star but a time-dependent path through a galaxy. Mergers take that path in their hands and redraw it. They shuffle where the radiation field strengthens or softens, where clouds crowd or thin, where chemistry is metal-rich or poor, where magnetic scaffolding channels particles or lets them diffuse. Worlds rarely fail in a single blow, they are nudged, season after long season, until atmospheres, oceans, and crusts settle into new equilibria, or do not. The same encounter that blasts a nucleus and strips some atmospheres also flattens metallicity gradients, seeds new disks, and mints future rocky planets with generous budgets of solids. Threat and opportunity are the same process viewed on different timescales. Return to your frame, two galaxies mid-collision, a single star carving a glowing spline, a planet's air drawn as a razor line with a faint sodium wake, and add one last layer that is true to the physics and generous to the imagination. Let the spline thicken where the star crosses a dense lane, grain with sparkles after each cloud-induced micrometeorite burst, narrow in the quiet halo, kink subtly where a bar resonance kicked its actions, and finally smooth as it joins a young inner disk. Let the atmosphere's wake brighten and fade with the background wind, let auroral curtains arc farther equatorward in the harsher chapters. This is not ornament, it is a readable logbook. Galaxies merge, stars migrate, planets rewrite their weather and their odds. The end state, a red spheroid with or without a blue disk, matters. But the lived story, for any ocean or sky, is the crossing itself.